educational videos by mmsprogramcivil.com. Please visit website mmsprogramcivil.com for all videos. Okay. Design of two-way slab. When a slab is supported on all sides, then the deformed surface of the slab will be doubly curved with load effect transferred to all the four supporting edges, right? So this is your rectangular slab. A is your shorter span, that is Lx. B is your longer span, Ly. Okay, and it is supported on all the four sides. When it is loaded with a UDL, then you can see you will see that this will have a doubly curved shape, right? Such action is called as two-way action, involving significant curvature along the two principal orthogonal directions of the two principal moments mx and my at the midpoint. Mx is along the shorter span and will be invariably greater on account of the larger curvature. Okay, so we can see over here, okay, when this slab is loaded with a UDL, okay, and the deflection at the midspan is delta, you can see the curvature along the shorter span is greater than the curvature along the longer span, right? And that is why moment mx will always be greater than the moment my. Okay, mx is the moment along the shorter direction, my is the moment along the longer direction. Okay, I have taken a small element at the midspan over here. Okay, so mx is the moment along the shorter direction and my is the moment along the longer direction, right? When the aspect ratio largest span to shortest span is greater than 2, then the curvature in the longer direction is found to be very small and can be neglected in design. That is, M by will be very small and can be neglected by providing minimum reinforcement as suggested by the code. Such slabs are designed as one-way slabs, right? Okay, fine. When your aspect ratio, that is B is largest span is Lx, Ly is by Lx, this is shorter span is say Lx, okay, you can say A. Okay, when Ly by Lx is greater than 2, then this curvature along the longer span direction will be very small and it can be neglected. So the moment along the longer direction my will also be very small and can be neglected and can be taken care by simply providing the minimum distribution still required in this direction, right, as suggested by the code. Okay. Two-way simply supported slab. The thickness of the slab is generally based on deflection control criteria, and the reinforcement in two orthogonal directions are designed at the critical section. The slab thickness should be sufficient enough to take care of shear, although shear usually is not a problem in two-way slab subjected to uniformly distributed load, right? Analysis of two-way slab. The bending moment in x and y direction can be obtained from the following equation prescribed in IS 456-2000, which are based on Grashof theory. Mx is equal to alpha x w into Lx square, where w is the load, okay, that is in kilonewton per meter square, okay, where Lx is the effective shorter span. Similarly, my is equal to alpha y into w into Lx square. Okay. Based on the above equation, tables are prepared in subsequent section to calculate the bending moment in x and y direction. Slab thickness based on deflection criteria. Okay, code is given some criteria through which you can start with an assumption of a two-way slab, that is for effective depth. Okay, for two-way slab of shorter span up to 3.5 meters with mild reinforcement and span to overall depth, that is L by capital D. Ratio given below may generally be assumed to satisfy the vertical deflection limits for loading class up to 3 kilonewton per meter square. Okay, So for simply supported, code is suggested L by D ratio is 35, continuous L by D ratio is 40 when you are using mild steel reinforcement. When you're using high deform bars, that is grade FE 415 or FE 500, you can multiply this by zero point 0.8. Okay. So this is a criteria through which you can start the assumption of a two-way slab, because slab are thin members and they and their depths are governed by deflection criteria. So usually in practical field, or usually in practice, to start with, span by depth ratio of the two-way slab is assumed within the range of 28 to 35. Okay. Expression for load on beam in a two-way slab. Okay. So two-way slabs are supported on unyielding support like walls or very stiff beams on all the four sides. The load distribution of the two-way slab to be to the supporting walls or the beam is as shown below. So this is a very important assumption, that the slabs have the support of the slabs on its all the four sides should be very rigid, either it is a beam or a wall, then only this load distribution is valid. Okay. Okay, we can see over here uh, that this portion will pass on the load, transfer the load to this shorter beam. This portion will transfer the load to this long span beam, and this again, this area of slab will transfer the load to the shorter beam, and this area of slab will transfer the load to the this long span beam. Okay. So the loading type of loading on the shorter span will be triangular. Okay. And a loading pattern on this longer span beam will be trapezoidal, right? So it becomes very difficult to do the analysis of such type of loading. So you can convert this to equivalent UDL, right? This can be converted to equivalent UDL with this formula, that is uniformly distributed load on beam in shorter direction. This is the formula, right? And you can convert this load into equivalent UDL using this formula: uniformly distributed load on beam along long direction, WY. Okay, so this is the formula. Over here, K is the aspect ratio, that is Ly by Lx. Okay, so this is a very important assumption that is made over here, that the slab is supported on rigid supports. Okay, then only you can do such load distribution, right? Fine. Okay, so there are two types of slab. One is slab supported on walls. Okay, these are known as simply supported slabs, two-way slabs. Okay, when they are loaded with UDL, then you can see they deflect like a saucer shape, take a saucer shape, and the corners are uplifted, right? So this is one type. Second type is when the beam and slab are casted monolithically, that is two-way slab with corner restraint as shown in figure below. Okay, so when they are casted monolithically, then there will be no uplifting of corners, and so you will have cracks in this direction and in this direction. So for that, to avoid this crack, you will have to provide reinforcement in this direction and this direction. So you will have to provide a mesh like this, right, at the corners, to avoid this cracking, right? It may be noted, however, that if the beam are provided along the column line and if these beams are sufficiently rigid, then the analysis and design of the slab can be considered separately and treated in the same manner as wall supported wall slab. Otherwise, the entire floor system, including beam column, will act as one, and slab cannot be analyzed and designed separately. This is very important. Okay. So the basic assumption is that the slab is supported on a rigid support, right? Then only you can do the design and analysis of slab separately. But if the support is flexible, right, or elastic, then in that case, you will have to do the analysis and design of slab, beam, and column together as a one unit. That is as in case of flat slab. Okay. Okay, so this is one type of reinforcement orientation that you can give at the corners. Alternate arrangement is very commonly used practical in a practical field with reinforcement placed orthogonally, making a mesh at top and bottom as shown in figure below, right? So this is how we provide, this is known as torsion reinforcement, which we provide at corner. Okay. So at the when at the corners, okay, where the two adjacent edges are discontinuous, you will provide 0.75 times the AST x positive maximum. So maximum still will be along the shorter direction, right? So you have to provide at least 75 percent of this steel, okay? That is both, you have to provide a mesh, okay? In that is both direction, and that also at top and bottom of the slab, okay? When you have one side continuous, then this area of steel to be provided over here is 0.75 into AST x positive. So over here we have two slabs. This is a common edge, right? You have slab 1, slab 2. So which ASTX positive will you will take? So you have to take maximum of this two, right? And the length of this mesh should be point 2 LX. Okay, this should be point 2 LX. This should be point 2 LX, right? Where LX is the shortest one. Okay. uh, Over here, where there is continuity on all the four sides, then there is no torsional reinforcement required, okay? Because the bent up bars which come at this junction from all the side, that is the top steel due to which will be the top steel of this junction, right? Okay. Some bent up will come from this side, 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 similarly here, and so on. And that top reinforcement will be enough, more than enough for stopping the development of the cracks at the corner, right? Okay. So this corner is this corner, okay? So you can provide U bars like this and U bars like this. So this will give you a top mesh and bottom mesh, right? So this is how you can do the steel design or detailing, steel detailing for this torsional reinforcement at the corner, right? Okay, standard reinforcement detailing of a two-way slab. Okay, when you take section over here, so this is the standard detailing. This is something which we already saw in case of one-way continuous slab, right? Only thing is that this dot in that case where distribution steel, over here in this dots will be the main steel in y direction. That is ASTY. Okay. Okay, so the following 9 conditions are given in the code as shown in figure below. The numbers denoted in the slab indicates the type of the condition of the slab, right? One is interior slab, so this is continuous from all the four sides. Then second is one short edge discontinuous, that is two. This one short edge is discontinuous, otherwise it is continuous from all the sides, all the three sides. One long edge discontinuous, so this is one long edge discontinuous, and otherwise it is continuous from all other three sides. Two adjacent edges discontinuous. Four, two adjacent edges discontinuous. Five is two short edge discontinuous. So two short edges are discontinuous and continuous on the long edges, right? 6 is two long edge discontinuous. So two long edges are discontinuous and two short edges are continuous. Three edges discontinuous, one long edge continuous. So three edges are discontinuous and one long edge is continuous. Three edges discontinuous, one short edge discontinuous. One short edge continuous, right? So one short edge continuous and three other edges are discontinuous, and last one is four edges are discontinuous, that is a individual slab, okay? So there are no slab around it, fine. Note all the conditions, all the continuous edges are considered to be fixed and all the discontinuous edges are considered to be simply supported. This is what this is an on this, the coefficient given in the code are on this assumption, right? Okay. Moments per unit width are given by the following equation. Okay, this is the following equation given in the code, right? Mx is equal to alpha x into wx lx square. My is equal to alpha y into w lx square. Okay, now so this is a two-way slab. Okay, so we'll come to this. So this is the table 26 given in the code. Okay, bending moment coefficient for rectangular panel supported on four sides with provision of torsion at the corner. So this will follow the following condition, that when the corners are not restrained against uplifting. So this, okay, when this is the case, you have to use this table 26. And when the corners are allowed to uplift the simply supported slab, two-way slab, then for that case you have to use table 27, right? So now we are focusing on table 26, right? So let us come to table 26 given in the code. So there are nine conditions, and for nine conditions, different value of alpha x and alpha y are given over here. Okay, so this are aspect ratio, that is Ly by Lx. These are the different conditions. First is the interior panel, and second, and so on, right? Which we already have seen. Okay, now this is shorter span coefficient alpha x. This is long span coefficient alpha y, right? We can see over here there is negative moment at the edges, that is alpha negative, alpha x negative, and this is positive moment at midspan, this is alpha x positive, right? So let me show you what is alpha x negative and what is alpha x positive. So let me come to this figure. Okay, this is your shorter direction Lx, this is Ly, right? So this will give you mx, that is moment along the x direction. So negative moment will give you the hogging moment, that is that will give you the steel at the support, and that, and this, as this is a negative moment, so the tension tension will be at top, and so the main steel will be at top, right? Over here and over here, right? Similarly at midspan, over here you have to use alpha x negative, and at the midspan you will get a moment over here and moment over here, that is along the shorter direction, that will give you positive moment mx, and over here you have to use alpha x positive, right? So this will give you a sagging moment, this will give a hogging moment, right? So over here the main steel will be at top, and for this the main steel will be at bottom, right? Similarly in y direction. Okay, so this is alpha y negative, this is alpha y positive. So this is where you have to use minus alpha y, and for positive moment you have to use plus alpha y. Okay, so this is how you have to, you can find the moments at the uh, supports and the midspan, and for which you have to do the design of a two-way slab, right? Fine. Now, this is the table given bending moment coefficient for slab spanning in two direction at right angles, simply supported on all four sides, which I just show. As it is simply supported, simply supported, so there will be no negative moment on the on the edges. Okay, because it is simply supported, so you will have only positive moment in two directions. One is along x smaller direction, that is moment along the smaller direction, shorter direction will be mx. For that you have to use alpha x, and design moment along the longer direction will be obtained by this alpha y, right? This is the graphical representation for alpha x and alpha y, right? Okay, in case of a simply supported slab, code says at least 50% of the tension reinforcement at the midspan should be extended to the support. The remaining 50% should extend to within zero point 0.1 Lx to zero point 0.1 Ly of the support as appropriate, right? Okay, so this is a simply supported two-way slab, right? So this is our maximum ASTX and ASTY, right? And at support, 50% of this has to be taken to the taken as a bent up at the top, right? From a distance, the bent up has to be taken at distance zero point 0.1 Ly and 0.1 Lx. Okay, so this is, you can see over here at center it is 100% AST, and at support 50% has to be taken, right? Similarly over here, AST, and at support you have to take 50%, right? So one straight, one bantam, one straight, one bantam. So you will have 50%. 50% of the main steel is taken at the top. Okay, fine. Okay, this is a very another important aspect. Okay, your slab can be supported on masonry like this, or on beam over here like this, right? This is section 1-1. This is section 1-1. Okay, so design negative moment at continuous support. When the two adjacent spans are not equal, these two spans are not equal, or the loading on the adjacent span is not the same, or the loading is not the same, or the boundary conditions of the two slabs are not the same, boundary conditions of the two slabs are not the same, then the negative moment at the common continuous edge will be different. Okay, so the moment at the continuous common continuous edge will be different, right? So this will have, say, moment left, this will have, say, moment right, right? So as the conditions are different, loading is different, or the spans are different, so you will have one ml and another mr. Okay, since the code coefficients are based on inelastic analysis, no redistribution of moment is permitted. Okay, permissible, you can say. Hence, it is logical to take the larger moment as the design negative moment at the continuous edge. Okay, code says that you cannot, whatever ml, mr, mr you get, you cannot redistribute. Okay, so you have to design this support, or you can say junction, for the maximum moment. That is maximum of ml or mr, right? Fine. Okay, so that is what the code says. Okay, another important assumption which I have already mentioned above, the slab is supported on beam that have to, then they have to be rigid enough. Okay, the support system has to be rigid. Okay, then only all this thing is permissible, right? Then they have to be rigid enough so that the torsion effect can be neglected, as the moment coefficient given in the code are for slab supported on walls. Okay, okay, so how to choose a rigid beam? Okay, so there is some practical aspect. Okay, in practical field, for the beam width, the beam is kept as 230, 250, or 300 as per width of the partition wall or column. For the depth of the beam on practical field, is at least assumed in inches equal to the length in feet, right? Say, what does this mean? Say the length or the span of a beam is 20 feet, then the depth to be assumed should be at least greater than 20 inches. Say it is 21 inch or 24 inch. Okay, that is a practical aspect on practical field which usually structural designer choose. Okay, for assuming the depth of the beam. Okay, so let us start with the problem. Design a two-way slab S1 with corner restraint as shown in figure below, showing its reinforcement detailing. Live load acting on the slab is 5 kN per meter square, and dead load due to floor finish and partition, that is furniture partition, wall is 2.5 kN per meter square. Take concrete mix as M20 HYSD bar FE 415 for design. Okay. So assuming the effective depth span by Lx by D is 28. Okay, this is for continuous two-way slab, right? Where Lx is 3.5. This is Lx, this is Ly, right? I'm going to assume my effective depth D is 125 and I'm assuming that I'm going to use 10 dia bar as my main steel. So half the dia bar plus clear cover 20 when I add to this, it becomes 150. So overall depth is 150. Self-hit, you can find this 3.75 kN per meter square. Total design load is 1.5 into live load into dead load into self-hit, that is equal to 16.875 kN per meter square. I am rounding it off to 18.5 kN per meter square, that is considering the weight of ceiling plaster. Okay, you can take 1% of the dead weight, right? Now, as it is a case of two-way rectangular slab supported on four sides with provision of torsion at corners, we will refer to table 26 of appendix D, condition 4. Okay, so this is condition 4. Two adjacent edges discontinuous. Okay, so let us see table 26. table 26. Okay, so this is table 26. Okay, table 26, right? This is the case. Two adjacent edges are discontinuous. Okay, so this is what we will see. Okay, fine. So now let us find the aspect ratio. Aspect ratio. Okay, aspect ratio that Ly by Lx is equal to 1.428, which is less than 2. So it will be designed as a two-way slab. Okay, so 1.428. So for that we will have to see 1.428 will fall between these two. Okay, so you will have to do interpolation of these two for finding alpha x negative and alpha x positive, right? Alpha x negative and alpha x positive can be found by doing the interpolation, because 1.482 will fall between these two, right? Okay, uh, this will directly give you alpha y negative and alpha y positive, right? Fine. So I have made a table. Okay, this is a table, right? So I got alpha x positive as 0.054, alpha x negative as 0.072, alpha y positive is 0.035, alpha y negative is 0.047, right? Now we can find the moment using this formula. Okay, so mx positive is 12.18, mx negative is 16.32, my positive is 7.93, my negative is 10.67. So let me show you what is mx positive and mx negative. Okay, so mx negative can be seen over here. Okay, in this figure, this is mx negative, this is mx negative, this is mx positive, this is m by negative, this is m by negative, this is m by positive. Okay, so mx negative will give this reinforcement at the support, m by negative will give the negative steel at the support. Okay, that is top steel. Mx positive will give the bottom steel along the shorter span. M by positive will give the uh, positive steel at the bottom along the longer span, right? Okay, so let us see the detailing part. Okay, fine. So you can find, once you know the moment, you can use this formula, because our is a rectangular singly under reinforced section. Okay, and using this formula you can find the steel. So for ESTX positive, this is the required steel, and we are going to provide 8 about 150 center to center, right? So this is our slab, this is our corner slab, right? So this is your shorter span, this is your longer span. Okay, so the main steel is going to be along the shorter span. Okay, so this is the steel for mx positive. So we are providing 8 about 150 so provide one straight bar, another bent up bar, right? So this is how we show the detail, right? Now similarly we come to mx negative. So for this is still required, and we are providing 110 plus 188 alternately about 150 center to center, right? So this is top steel, right? So mx negative will give a hogging moment, for which we have to provide steel at the top. Okay, so this bent up will go at top. So this is 8, this is 8 bar. Next to it, at a distance of 150 provide an extra 10 dia bar, right? So you can see this bar is this bar, this bent up is this bent up, right? So this is the steel at top. So this is the steel at top, and this steel which we provide at the top is 110 another 8 bent up plus 110 then 8 bent up, and this is provided at a center to center of 150 Okay, so this is how which we provide the steel at top and bottom along the shorter direction, right? Similarly, along the longer direction, EST Y a positive is 190 square is still required. We will provide 8 dia bar about 180 center to center. So this is the steel along the longer direction. We will provide at midspan 8 dia about 180 center to center, right? So one bar is straight, another we take a bent up, straight, bent up, okay, like this, right? So ESTY negative required is 258. And again, we are going to provide 8 about 180 center to center, right? So in that case, you have one bent up of 8 provide additional extra bar of 8 at a distance 180 So this is how you will have 8 about 180 center to center, right? So this is how we provide the steel, right? Okay. So these are some basic formula which I have shown over here. How to find spacing or how did I find the spacing, right? Spacing can be found by this formula, that is area of one bar into 1000 divided by AST. Okay, so this is the AST. So once you find the spacing and you fix some spacing, say I fix the spacing to 180 then after fixing the spacing you can find AST provided. In that case, AST provided you can find by putting over here your spacing provided, right? So area of one bar into 1000 divided by spacing provided will give you the AST provided. This is AST required. Okay. Once you finalize the spacing, you will get AST provided. Okay. So you can find AST provided. Fine. Now details of torsion reinforcement top and bottom mesh. Okay. So over here, we will have to provide for this distance 0.2 LX and 0.2 LX. Okay, LX is the shortest span, right? You will have to provide 0.75 into ASTX. This is your ASTX, right? So 0.75 into this area of steel, okay, 0.75 into this area of steel, okay, that is equal to 283, right? So this is the steel required, okay. We will be providing top and bottom mesh about 8 about 200 center to center. And so the EST provided in each direction in mesh will be 251.4 square, right? So at this corner, okay, we will be providing 8 about 200 center to center. So let me show you over here how you can do the detailing of this. Okay, let me come to the figure. Okay, right. So provide these U bars at 200 200, 200, 200, 200, 200, 200, 200, and 200. So this will give you 8 about 200 mesh at top and bottom of the slab. Okay, so this is how we can provide, right? So let me now come to the next step. Okay, then we come to the edge where one edge is continuous, right? So what there we have to provide. Now we are coming over here, right? So this is 0.2 lx, this is 0.2 lx, this is 0.2 lx, right? This steel, this area of steel in this match should be 0.375 x positive, right? So you have to take maximum of this positive or this positive. But at present we are designing only this slab, so we don't know the steel for this slab, right? But so we will carry on with the ASTX positive, ASTX positive of this slab, right? Otherwise you have to take the maximum of this two, right? So that is equal to okay, 0.375 is equal to 106. So we will be providing 8 die about 300 center to center mesh, right? So let me show you the figure again. Okay, so 8 about 300 center to center, coming to that figure again, right, okay. So we here you have to provide 8 about 300, 300, 300, 300, 300, 300, 300, and 300. And same thing, this is now we are having a continuous one. The slab is continuous on one side. Okay, there is another slab over here also. One slab is over here, one slab is over here, one over here also. So same thing is to be repeated on over here also, right? Okay, so this is how you will get uh, the steel detailing for the continuous edge, right? Okay, this is how you will get the detail, steel detailing for this area, right? Okay, this is over here. The slab is continuous from all the four sides. Okay, this junction, you have slab on this side, you have slab on this side, you have slab on this side. So there is no need for additional torsional reinforcement. Okay, whatever the bent ups which are coming from this bent up will come from here. This bent up will come from here. Another bent up will come from here. Another bent up will come from here. So this top steel will take care of the uh, corner cracks, right? That will be enough, more than enough. Okay. No additional torsion reinforcement has to be provided in such at such junctions, right? Okay, fine. So everything is shown over here. Okay, this distance should be greater than zero point 0.5, 0.15, right? So this line is shown for the bent up. Okay, okay. This line is shown for the bottom. This line is shown for the extra top. Okay, this shows the length. Okay, similarly over here also, right? So this is how you do the detailing of a two-way continuous lamp, right? Okay, now we have to do the check for deflection. Okay, uh, so the allowable span to depth ratio is obtained. L by D allowable is L by D basic into KT into KC. L by D basic for two-way continuous slab we can take as 26. For finding the modification factor for tension reinforcement KT of shorter span, first we are taking shorter span. You can find the stress in steel by this formula. The stress in steel using this formula is found to be 202.72. So this will fall between these two graphs. Okay, and for the percentage of steel, um, AST X provided is 336 mm square. So our percentage of steel is equal to 0.2688. For that, you get corresponding KT from the graph as 1.85, and Kc is equal to 1 because there is no compression steel. When there is no compression steel, Kc will be equal to 1. Okay, so allowable span to depth is obtained. This is 26, this is 1.85, this is 1, so this is equal to 48.1. And actual span by D, that is Lx is 3.5 meters, D is 1.25 mm, so this is 28, which is less than 48.1, so it is safe. Okay, for longer span, you find your stress in steel is this much, 163.72. PT is 0.2327. For that, you get KT is equal to 2. You can, from KT is found to be something like 2 over here, right? You can check this by your own, right? It's simple, it's very simple. I already explained in last chapter, that is design of one way continuous lab, right? So KT is found to be 2. So the allowable span to depth ratio is found to be 26 into 2 into 1, that is 52. Actual span by D ratio is Ly is 5 meters, D is 120. So this is 41.66, which is less than 52. So that is found to be okay. Okay, it's satisfies the deflection criteria. After that, the another important check is check for one-way shear in the slab about the shorter span, right? So this is the critical section 1-1 for the check for one-way shear, which is taken at a distance small d, effective depth d, from the support. So we'll take 1 meter strip, and the length of this strip will be this is Lx, so 0.5 Lx minus d, this is 0.5 Lx minus d, this is 1 meter. So we will find the shear acting at this cross section for this strip. that the shear acting at the cross section will be W is the load into the area of the strip. Okay, so this is your shear force acting over here, right? This is W into area of the strip. So that is equal to 30 kilonewton, right? The percentage of steel which we are providing, tensile percentage of steel that is provided, that is to be taken at this cross section. At this cross section, the top steel will be the tensile steel because it is near the support, right? So the percentage of tensile steel over here is 0.2327, right? So from table 19, for this percentage of steel, tau c, that is permissible shear stress, is found to be 0.355. You can find the nominal shear stress V divided by BD. V we know 30, so that is 0.24. 0.24 is less than 0.355. So tau V is less than tau c. So the section is safe under for the shear criteria, right? So please visit website mmsprogramcivil.com for more educational videos. This video is uploaded on the same website. I hope you must have found this video useful. Thank you.